In this lecture, we're going to look at the chemistry of ethers, and that is specifically the reactions of ethers. So, getting that kind of framework in our heads, what types of chemistry, what types of transformations can ethers do? And a big one is the reactions with halo acids. And so our halo or halogen acids, this would be like HCl, HBr, HI, HF. It turns out HF doesn't really do this chemistry, so we can cross it out for the most part. There are some special circumstances. HCl is kind of pretty sluggish. HBr is the winner here because HBr is the real winner, but HI can also participate in this reaction. But recognizing HCl could be a possibility is important. Okay, so anyway, what do we do with ethers and acids like HBr? Well, if we take diethyl ether, that's a really good starting ether to consider. We can react that with HBr, and then the products of the reaction will be ethanol and bromoethane. So we get two products. Okay, now I've emphasized this before, but for us to understand this mechanism, or excuse me, this reaction, we don't want to memorize these two products necessarily. We want to know the mechanism. Study the mechanism. Oh. Study the mechanism. Okay, so what's the mechanism for the reaction of ethers with halo acids? Okay, so I could just present the mechanism step by step and then ask you to memorize, but I want to try to introduce some strategies to think about. First of all, halo acids are strong acids. And what this means is that they react first to release H plus. Okay, so H plus, whenever we have an H plus in our mechanism, H plus generally reacts first. So most of the time, H plus reacts first. So what we have to consider then is, for starters, in our reaction, we had HBr, and that exists in an equilibrium that's probably favorable where the H plus and the Br minus are dissociated from one another in the solvent medium. We could draw curly arrows for that, where the electrons between the hydrogen and the bromine jump over to make a new lone pair on the bromine atom that already had 3 lone pairs. So now it has 4. Its formal charge is -1. The formal charge on the hydrogen without any electrons is +1. Okay, so this forms right away. Now, it's important to remember that H plus is a single subatomic particle. So of all the things that can react, H plus is the most versatile. It can find its way in all the nooks and crannies of the reaction and engage the molecules that we're interested in. Okay, oftentimes I don't draw this. I don't often draw this. You can if it's helpful, but I remember that HBr is a strong acid. I should add like a little adage here. I'm going to put a little box. Okay, strong acids. We're going to do a lot of chemistry with strong acids, and strong acids automatically make H plus. Now, you've probably been exposed to these in your other classes. These are just things that in water form H plus very easily. They are HCl, HBr, HI, so our halo acids. H2SO4, that's sulfuric. H3PO4, that's phosphoric. And then HNO3, that's nitric. I would know these, not just for this class, but for chemistry in general, for your chemistry education in general. You should know the strong acids. And so I keep these 6. Are there others? Sure. There's like perchloric and tetrafluoroboric or something like that. But those are all acids that are fairly specialized. And at this level, I would say just knowing these are often called the mineral acids. Interesting names, whatever. Just know that when they are present, you've got H+. You've automatically got H+ in your mechanism. And H+, that's a really good hint because H+ reacts first. So I often don't draw the very first step where the H+ dissociates from the bromine, but instead I'm going to start the reaction and say I've got H+, and this is from HBr. I've got Br-. Br- isn't going to do anything in this first step. And then I've got my ether. Now the H+ is desperate for an electron from somewhere, okay? It just gave its electrons to Br-, so getting those back would just be a reversible step. Instead, we're going to take electrons from the ether oxygen, either one of those lone pairs of electrons, and that's going to engage the H+ to make a new covalent bond. We could draw the bond either on top or on bottom. Probably looks better on bottom, and then we just let the lone pair sit up there. That looks a little bit more appropriate for the geometry. But in either case, the oxygen, after it reacts with the hydrogen, now has a positive formal charge. And we could do that formal charge calculation quick. We've got a group 6 element, -3 bonds, -2 electrons. That's equal to +1. Okay, so let's recognize that protonated ethers are +1 on oxygen. Protonated ethers are +1 on oxygen. I just did that with the formal charge calculation. And if you haven't heard that term before, I'm not sure, but protonated, that's equivalent to saying that we reacted with H+. Now, H+ is a single subatomic particle. It's just a proton, right? It doesn't have any neutrons. It doesn't have any electrons. Well, it doesn't have any neutrons for the most part. We assume that we've got greater than 99% hydrogen. Okay. So we've got H+, engaging our oxygen to give us a new intermediate. I'm going to redraw that intermediate down here. So it's ether. We've replaced one of the lone pairs with a hydrogen. The oxygen only has one lone pair left, and the formal charge of this is positive. So we have a positively charged oxygen atom and a Br- that's desperate for some sort of positive charge so that it can neutralize its negative charge. So what's an approach to get rid of that negative charge? Well, opposites attract, right? Maybe you want to let the negative engage the positive. Here's the problem. I'm going to just get red all over this quick so we don't see, but this is not a good arrow because look at the resulting structure. The resulting structure has oxygen with 10 electrons, and that exceeds the octet rule. So it has 10 electrons. How do I know it has 10 electrons? It has 4 bonds. Each of those provide 2 electrons. So we have 8 electrons from bonds. And then we still have that lone pair of electrons giving us 10. As a row 2 element, oxygen cannot exceed the octet rule. Okay, so we can't directly engage the oxygen, but we do have another opportunity. We could engage the carbon next door to the oxygen. It's already got a delta positive. And that delta positive is probably stronger because the oxygen next door is even more electron deficient. And so it's probably tugging on those sigma bond electrons even more strongly. So what we're going to do is engage the carbon next door to the oxygen and push the electrons onto the oxygen atom to give us this structure. And if you look, these are our 2 products. So what did we do? We added to the carbon. The bromine added to the carbon next door to the oxygen. That carbon then would exceed the octet rule, so it's going to immediately dump its electrons onto the oxygen atom to neutralize the oxygen. Everything is now neutral. The bromine atom now has a bond, so it's a bond with 3 lone pairs. So as a group 7 element, that would be a 0 formal charge. Oxygen similarly is a group 6 element with 2 lone pairs and 2 bonds, and so it also has a 0 formal charge. Get comfortable with the formal charges, and then get comfortable with kind of how we push the electrons. We're going to use 2 arrows for this mechanism. Now, we've formed our products. The mechanism is complete. So the mechanism is complete, but we should note that Br minus could attack either side. What do I mean by either side? Well, if we look at our ether molecule, it's actually got carbons on either side of the oxygen. Right, we've got a delta positive on either side, and so the bromine atom could attack the right or it could attack the left. So we're going to add to the delta positive carbon on the left this time. To avoid breaking the octet rule, we're going to push electrons from that carbon-oxygen bond onto the oxygen atom. That's going to give rise to these 2 molecules. Well, if you look, compare the outcomes here. The 2 sets of products that we formed were the same, okay? When I originally presented this reaction, I said that we form 2 products. We have ethanol and bromoethane, a haloalkane and an alcohol. But what if we, but in reality, we actually form 4 products. It's just that 2 of them are the same. The reason why they're both the same is that diethyl ether was symmetric. So this molecule has a plane of symmetry. This is symmetric. And what that means is attacking the left and right gives the same product. Gives the same product. Okay. So what if we make it, what if we lose that symmetry? Let's make one side a methyl group and the other side an ethyl group. This would be ethyl methyl ether if we're trying to name this. We're going to react this with a halo acid, and let's pick HI in this case. And so here I'm not even going to give us the products. So sometimes I want us to propose a mechanism with the products in hand. Sometimes I want us to propose the products. In both cases, we do need to consider the mechanism. This is an example where I want to go through the mechanism to make sure I know which products are being formed. Okay, so what's the mechanism? So we're attacking this mechanism first. Well, first of all, let's recognize that HI is strong. So it's not like we're really using HI in this reaction. We're using H plus and I minus. Okay, that's important to note because the reaction is really this. And the first thing we want to do is let the H plus engage. It's just a subatomic particle. Just let it do its thing before anything else, because everything else is a little big and a little sluggish. To do that, we're going to neutralize the positive charge on the hydrogen by letting the oxygen lone pairs add to that hydrogen atom. It's going to give us a positive charge on the oxygen. And then the iodine is going to have a choice. It can add either to the left side or the right side. I'm just going to scroll down and redraw this. You may not need to. So if I have my protonated ether, right, because we've accepted a hydrogen atom, then the iodide could add to one of 2 sides. We could add to this side. I'm going to call that path A, or we could add to this side, and that's going to be path B. If we add to path A, we'll push the electrons onto, need my positive charge here, that positively charged oxygen. Adding to path B would push the electrons over here onto the oxygen. Now, if we go through route A, we're going to keep the carbon-oxygen bond on the left and break the carbon-oxygen bond on the right. That's going to give us these 2 products. If we go through path B, we're going to break the carbon-oxygen on the left and leave the carbon-oxygen bond on the right. Got Got to make sure I don't, it's just a CH3 group. So I should just go like this. I could even write CH3 if I need to make sure I don't forget it. It gets kind of tricky if it's at the end of the chain. Notice how I'm kind of drawing my product strategically so I don't accidentally add or delete carbon atoms. But these are now the 4 possible products that are formed. So what we show here is that if you have an opportunity to do this reaction on a molecule without symmetry, then you will see multiple products being formed in most cases. There are some examples where we'll see you can actually not form something on the left side or the right side, but we can touch on that in the next lecture. So this is kind of the basic mechanism for the first reaction for first reaction of ethers, halo acids. We typically don't do this with any of the other strong acids because what the problem is they don't have what's called a nucleophilic conjugate base. So that conjugate base that results, in this case, it was iodine minus or Br minus. Those are fairly nucleophilic still, if you remember from SN2 stuff in organic 1. Don't worry if you don't, they're nucleophilic enough. If you look at the conjugate base of nitric, phosphoric, and sulfuric acid, those aren't nucleophilic enough to engage an electrophile. Okay, so that'll do it for this lecture.